welcome to the Graph Algorithm playlist. Hello. After discussing about spanning trees and realizing how each spanning tree will have its own cost for the span, we finally arrive on the topic of minimum cost spanning tree. Now, the minimum cost spanning tree has its various obvious applications, but let's first dive into the intuition behind the algorithm which will give us the minimum cost spanning tree of a graph. So let's build our intuition with the help of an example, with the help of a simple graph. So here is a graph with the weighted edges as shown. We have the weight of the edge 3,5 as 6, and the weight of the edge 3,1 as 17, weight of the edge 1,4 as 10, and so on. Now, to get the minimum costing span, we will get attracted towards the edge with minimum weight for obvious reasons. So let's focus on this edge, which is basically the edge 3,5, which has the minimum weight out of all these edges, and it has length 6, weight 6. So let's focus on this edge and the vertices at its end, because vertices are the things we care for, right? Because we have to span the vertices, and then we will choose edges from these vertices only, basically. So we basically choose this particular area in this graph. Now we select this particular area, and looking at this neighborhood, now we have three edges which connect. So these edges either connect to 3, either connect to 5, or to both. So we have these three edges. Now to span 3 and 5, both the vertices, and to not miss any of those, because in any spanning tree of a graph, we never miss any vertex. We cover all the vertices. Hence, we need to pick at least two of the three edges here, so that both 3 and 5 can come into the traversal we are making. Hence, we obviously choose. So because you need to you are looking for minimum cost spanning tree. So after choosing the vertex, after choosing the edge which has length 6, we'll choose the edge with the minimum weight between the left two edges. So that's the edge with the length 7. So now our spanning tree, which is basically our tree, which will grow up to become a spanning tree, has got expanded, and now we have 3 points in our collection: point 3, 5, and 2. Now it's natural that our focus now shifts on to the next obvious short lengthed edge, which is the edge which is the edge of length 10, the edge 1,4. But wait, why are we hurrying? See, in any spanning tree of a graph, we never miss any vertex. So it is 100% confirmed that we are going to arrive at this particular vertex at some point of time. And there are only two ways to arrive at 4. It's either 1 to 4 or 6 to 4. So we are basically, it's guaranteed that we will arrive at 4. So why are we hurrying, and why are we destroying our tree structure? Why don't we simply try to grow this tree structure and make it become a spanning tree? It's easy, right? It's easy, it's convenient. Why are we taking pain of basically destroying a beautiful tree structure? So we are anyways going to arrive on it, so we should consider it we can consider it later. So now we should basically focus on the edges which are connected to the collection of points we are having right now. And if you consider that particular area, so we basically get these edges in which are right now in our focus area. So it's obvious that out of these edges, the edge with the minimum length now, which has not been covered, is the edge with the length 12. So we choose the edge we choose the edge which has the minimum length, and that's basically the edge of length 12. Now our tree has expanded more, and its collection of points has increased, and now we have 3, 5, 2, 6 in our set. Now here is an interesting point. Although the minimum edge in this particular stage is 2 to 1, and that is of the length 15, but just for the let's just consider this particular edge 5 to 6, and we see that let's say if its length were to be 13, then you will definitely consider the edge 5 to 6, right? And in that particular case you'll consider the edge 5 to 6, but you'll see that the edge 5 to 6 creates a cycle, and a spanning tree cannot have a cycle because that's useless for a spanning tree. It's of no use, and a spanning tree is tree, so we can't have a cycle in that. So we will basically discard this edge. We are never going to use this edge. It's a useless edge. Now we were obviously we were although we were not focusing on the edge of length 19 anyways, because the shortest edge right now at this moment with for this collection of points is the edge 21 with the length 15. But let's say if there were a case where the edge 5 6 had a length of 13, then we would have considered this. So now we'll basically traverse to from 2 to 1, and of the for the edge of length 15, and now again we have two choices. One is to go from 1 to 3, and other is to go from 1 to 4. But again the edge 1 to 3 will create a cycle, and again it's of greater weight, so we are anyways not going to consider it. So we basically go for the edge 1 to 4, and we choose 1 to 4, and you can see that this way we have basically covered all the vertices. We have covered all the vertices what we have covered all the 6 vertices. So we'll stop here because we have covered all the vertices and we have covered in the minimum cost possible. So this is our spanning tree, or this is our minimum cost spanning tree. So, but we should just like how we discussed about the cycles, and how we also discussed how we covered all the vertices, we should first consider about the edge cases. Where can we go wrong? What can be that condition where we are calling the wrong thing as the minimum cost spanning tree? So there can be a case where we may create a cycle. So that's checkpoint number 1 for our algorithm. And there can be a case where we may miss any vertex. So that's checkpoint number 2 for an algorithm. So after considering these checkpoints, we create an algorithm with the first step, the initiation step. We can choose any random vertex, right? Just how we skipped the edge with length 10, because we knew that um, we are anyways going to come at we are anyways going to traverse that, and we are anyways going to consider that at some point of time. We can start from anywhere, so we can choose any random vertex. This is the initiation step of our algorithm. Now select the edge with the minimum weight connected to the vertex. So we chose a vertex, and now we'll select the edge which has the minimum weight connected to the vertex, such so that we are in the process of making minimum cost spanning tree. This is our optimization step, and this is the step which will lead us to get a global optimal solution. Now the third point, mark the vertex as visited. If you visit it ever again, that means you are constructing a cycle. So every time we visit a vertex, anytime we visit a vertex, let's say I go from the vertex 3 to 5, I'll mark in the structure where I'm listing the vertex, or where I'm storing the vertex, I'll mark that I've visited the vertex 5. So now if I again visit it, I'll know that I visited this vertex one time in the past, and hence I'm creating a cycle. I'm creating a loop, I'm creating a cycle, and that's not something which is allowed in spanning trees. So this is the step in our algorithm which will satisfy the checkpoint number one. Now follow this, follow the above steps, the step number two, step number three, until all vertices are covered. So now this will cover our checkpoint number two. Also, you will see that by the optimization step we look that since we look for immediate optimal solution at each step. So as we saw in the optimization step, we look for immediate optimal solution at each step. We chose a vertex, we'll choose the minimum edge connected to it. Hence this algorithm is a greedy algorithm, and that's why I introduced you to greedy algorithms few videos back. uh, so this algorithm is a greedy algorithm. This algorithm falls into the category of greedy algorithm. This algorithm uses greedy technique. And this is basically what is known as Prim's algorithm. So this is our famous Prim's algorithm, although the backstory is that this algorithm was actually founded by the Czech mathematician Jarnik in 1930 or so, and Prim and Dijkstra rediscovered and republished this algorithm, and that's why it famously is now known as Prim's algorithm. So also one more important point which which is obvious, is that cost of this minimum spanning tree, or MST, you can call it minimum cost spanning tree, minimum spanning tree, is the sum of cost of all edges, which is obvious. Now that is it for this video, and in the next video we'll cover some more algorithms, some more interesting algorithms. We'll cover the basic intuition behind these algorithms, and just like how we so basically this algorithm was discovered by Jarnik, and we basically went through a process of how Yarnik would have at that time, 70 years or 90 years back, how Yarnik would have thought about it and how Yarnik would have reasoned about it. And that is the goal of this playlist. The goal of this playlist is to go behind the intuition, and the thought process of the inventor itself behind these algorithms. So let's meet in the next video. Until then, peace out.